Good afternoon, everybody. I'm Dave Rugg. I'm a Rolls-Royce Fellow. I'll explain a little bit about what that means. And in the next 45 minutes or so, what I'm going to try and convince you is that, first of all, industry is actually quite interesting. We do a lot of fairly fun, techie stuff, or at least we need to drive a lot of technical stuff out there in the academic network and in national labs and such like. So there's a whole mix of stuff through this. It's definitely not a sales pitch for Rolls-Royce. So I think I've only got one slide that's actually about Rolls-Royce. Okay, so I'm not trying to tell you to come and join us. I'm not trying to tell you that our products are great, because it's unlikely you're going to buy a jet engine or a nuclear reactor. We don't do cars at all, right? So no cars. So this is meant to be a fairly generic talk about why industry is important and try and get the message across to you that physics and mathematics, that you can actually do an awful lot more than you actually think you can, and the applicability is much broader. Another very guilty admission here for you is I don't actually do any work. So all of the stuff that I'll talk about, all of the stuff that I'll show essentially is stolen from other people, and mainly my colleagues in academia that I interact with and have a lot of fun doing so. So right, let's just roll through. So I've got quite a lot of stuff in here, and it's kind of a bit random of what I've thrown together. There's loads and loads I've missed out, so kind of apologies for that if there's things that you're interested in that I don't cover. Plenty of time in questions and answers afterwards, but I'm going to try and go through this at a fairly rapid rate to get through it. So I'm going to talk a bit about me, a bit about Rolls-Royce, talk a little bit about the industrial backdrop of why there's complexity in what we do. Okay, so it's not a case of just banging nails into bits of wood and putting bolts and nuts and bolts together. I then got three specific case studies, which I've described as small and slow, big and fast, and small and fast. You may debate with me afterwards in physics terms that when I say small, I don't really mean small, and when I say slow, I don't really mean slow, but one thing, when I say fast, I do actually mean fast. So you can challenge me on that at the end. Summary, and then at the end, there's a specific question about recruitment and industry and how all that kind of works. And what I've done there, I've just got a couple of slides. Probably the most pertinent one is about what I actually look for when I'm recruiting people. I used to do a lot of that. I don't do so much now for various reasons that we can talk about in the questions and answers. And it's not quite what you think, so we can cover that. Right, so Rolls-Royce, this is the one Rolls-Royce slide, key facts. Really great, interesting place to work because we design and make jet engines and nuclear reactors. So the reactors, submarine reactors, so like civil PWRs, but they have all sorts of entertaining things associated with them. Like a civil PWR, you don't have to design it so it can operate upside down or if it gets step charged, which is kind of quite interesting. You've also got to cram it into a really, really small space. So all the fun of a civil PWR, but all compressed right down. So that's great fun. And I had about 3 years in the Reactor core group setting up the fundamental sort of academic research programs relating to materials and some physicsy stuff. I'll talk a little bit about that. We don't make cars. That's all gone. Went a long time back, different company. We've got about 40,000 people worldwide. We've got plants in a lot of countries, customer base all over the world, and about 24,000 of those 40,000, I think, are engineers, something of that order, give or take, maybe 20,000. Big company, so 73 billion order book, or indeed from the Trent 900s on the A380s that were announced earlier in the week. You can add on another 12 billion to that. About 15 billion turnover, around about 1.7 billion before tax. And then the fun bit, leave the fun bit to the last, about $1 billion a year on R&D. How good is that, eh? And the guy that looks after our R&D division, a guy called Rick Parker, is absolutely hysterical. Real fun character, and he's actually a laser physicist by backdrop, and he's got $1 billion a year checkbook to kind of spend on fun things that make us money as well, but there's a lot of fun in there. So in terms of the actual kind of different roles and things, because that was, again, one of the questions I was asked in there. Technical stuff matters, and the reality is that when we design new product, it's actually really hard. So if we do a sales campaign where Boeing or Airbus come to us and say, hey, we'd like a new engine, and they'll do the same with Pratt & Whitney and GE, And we want it to do this kind of flight cycle and da-da-da-da-da. What can you do? What will it weigh? What will the fuel efficiency be? So we then have this interesting thing where the project director will go around the different engineering groups in the company and say, okay, in fans, as an example, if you had, a couple of years and a bit of money, what could you come up with by way of improvement on the existing product designs? And they do the same turbines, combustion, all the CFD stuff that joins it all together. They'll then look at all of those things combined and then come up with an estimate of what the competition are doing. And they're smart, right? Because they've got thousands of engineers and spend lots of money in R&D. And they'll kind of then make a judgment in terms of, okay, will that actually be competitive? And if it isn't, they either need to make the decision, okay, we reckon the engineers are being miserable and they're being conservative and they can do a bit better if it actually comes to it. So we'll up the bid a bit in terms of how good this product's going to be. Or they walk away from it and they've got that choice. So you then have 3 potential outcomes when you go to the airframer with your bid. One of those is they say, sorry, you're just nowhere on this, you're not cost competitive, you haven't got an efficient product. And if it isn't an efficient product, people will not buy it. Okay, so there's a clue there, you go out of business eventually, quite simple. They can say, yeah, okay, we're fairly happy with the Rolls-Royce bid, and what we'll do is we will dual source engines for this aircraft. So we'll have GE and Rolls-Royce, or Pratt & Whitney and Rolls-Royce, and we'll do that. And the other thing they can do is if they're really, really impressed, they'll say, gee whiz, you Brits, absolutely incredible. We don't know how you can possibly come up with a bid like this. This is just absolutely outstanding. And the project director comes back and the sales guys come back all happy, and then they say to the engineering and science people in the company, great news guys, we're sole sourced on this engine. So on February the 22nd, 2020, all of these planes are going to be carrying people about all over the planet. You can buy your fares now for it. All you've got to do is deliver it. And at that point, we don't actually know how we're going to do it. Okay? Straight up, we don't know how we're going to do it. We haven't got millions of engines sat there on the shelf that we've designed earlier just in case somebody comes along. New engine project will cost 500 million plus to do. Okay, huge amount of work in there, and that's with massive barriers to market entry. The cost and infrastructure associated with doing that's huge. And here's the other neat thing for you associated with, right there, no problem, grab a seat. Here's the other really neat thing for you, is that it isn't all just deterministic. We don't have a kind of like a design model where we go, oh, let's just dial in this fuel efficiency and that and hit a button and it goes zzz, and here's your design. It's about people and about expertise and about skills. Okay, yeah, sure, absolutely, it's vast modelling capability, all the rest of it, but it's all about the people, and that's what potentially then differentiates you and keeps you in business. So, in order to then actually drive that, what I'm trying to say is technical stuff's important. So what we've got on here is engineering roles, and what you've got there is the sort of management-y type stuff in the middle, but it's virtually all technical in reality, at least within the engineering functions. And that's the heart of the company. Without that, everything else just falls over and fails, okay? You've then got the out and out what you call technical project managers, and these are an amazing bunch of people. They're the chief engineers. Okay, so they are absolutely accountable for that product. If something goes wrong with that, they're in court. Okay, and they are absolutely accountable. They're accountable for the organisational capacity and capability in that. For everything. If we're type certificate holder, it doesn't matter who we're partnered with, doesn't matter where we bought the stuff, all the rest of it, we're on the hook for that. The chief engineer is the person that goes to court. Serious business. If you do stuff wrong in this business, you kill people. The other side of it, which is where I've sort of ended up, is the fellowship. So that's the technical growth structure. And to give you an idea there, essentially you can stay doing the same kind of thing, same technical discipline, and you can ratchet your way up through the technical grades here. So I'm sort of fellow, and if all goes well in a couple of weeks, maybe senior fellow. And that's equivalent to chief engineering roles. And I have well, come on to the next slide. So what do? So I'm a specialist, full life cycle support for titanium, so that's the front third end of jet engines, and also do quite a lot on reactor core components, which are mainly made of zirconium because of the neutron capture cross-section, bit of physics there. Interested in everything, mechanical behaviour, processing, failure investigation. I also look after the define and run the what loosely termed the fundamental programs in academia. So that's across mainly in the UK, Imperial, Oxford, Cambridge, Manchester, but there's quite a few others as well, and some national labs as well, Berkeley and National Lab for Metals Research in Shenyang. I've got stuff going with. So at any given time, I've got sort of the order of 10 to 20 PhDs running. I've got no line management accountabilities either. Okay, so my bureaucratic workload is near zero on loads of steering boards and things. And the real fun thing is, and I've switched it off, I hope I've switched it off, my phone when it rings, it can be anything, literally anything. It can be somebody asking me questions about fusion. One of the steering boards is materials fission and fusion power, through to a chief engineer that's got a problem with an engine that's blown up somewhere in the world, and they want a view on what that is. One of the other things, I won't spend too long talking about this, I've talked about new product development. The next slide actually may do it. No, it doesn't. Right, let me talk about gas turbine very quickly. Absolutely amazing products, and every time I see one on strip, I'm amazed that you get design convergence for the thing to work. So to give you an idea of this, the energy density is similar to a Formula One racing engine, but the required reliability is phenomenal. I'll cover that in the next slide. So in total weight of about 3.5 tons, 50 megawatts produced from that. Power on the 3 shafts, about 240,000 horsepower. Max takeoff conditions, 23,500 cubic feet of air a second going through it. Everything in there is working really hard for a living. If it isn't, we haven't done our job properly, and we have to whittle mass off it. We have to design it better to make it more efficient. I've probably got a slide that talks about temperatures and load regimes and stuff. So let's talk about, in terms of reliability there, say the energy densities are phenomenal. I should have phased this so that these things came in. One of the metrics that we have, so this is no wiggle room on this, openly reported stats. Mean time between engine shutdown for our current portfolio is the order of 74 years. So if you had a single engine sat on the desk here running, or you watch one flying around, 75 years between the engine shutting down in flight for some reason or having to be shut down, which is pretty phenomenal. So that means a newly qualified pilot might have their whole career without ever actually experiencing an engine shutdown. It's quite likely. The other thing that we measure, and this is where it starts getting into the more serious side of it. For the core engine components in here, the things called discs that hold the blades on, these things are spinning at really high RPM. So this HP compressor in the middle here, it's about the size of a dustbin. Don't let the compressor people hear me say that, but about the size of a dustbin. It's spinning at about 10,500 RPM. If it fails, or any of the other discs in here that hold the blades on, there's so much energy that you can't contain them within the engine. Phenomenal amount of energy. You can do your MR omega squared or whatever it is, being physicists. So in layman terms, 7 Series BMW doing about 120 miles an hour, and you've got a couple of millimetres of aluminium between you and it if it goes bang. So if these things fail, they threaten the airframe, and that means not good at all. So when we certify, we have to demonstrate numerically that the probability of that happening is less than 1 in 10 to the 8 flights. And that's numeric demonstration. It's not kind of like, oh, we think it's all right. Here you go, authorities, as sort of a bit of a ropey case. We have to actually demonstrate. And by and large, the industry actually hits that. So if I took one engine and I put it on the desk here and I ran it up and down, one of the main threats is what's called low cycle fatigue, which is essentially centrifugal stress. It's actually far more complicated than that. So if let's say we did that once per hour and we just sat here and watched it, what would our mean time between uncontained part failure of that engine be? And it's 4,600 years. So this would be the most boring thing on Earth, and yet the energy density is phenomenal. So what do we make them out of? All kinds of fun stuff. Again, energy density, if you imagine unwrapping the core engine, folding it out and think about the load. So you've got about 3 tons of metal in there. Pretty neat metal, and I'll just go on to talk a bit more about that. You've got about 25,000 tons of self-load from CF hanging on that. And I can't remember what the next slide is, sorry, it's a while since I did these. Yeah, okay, we'll talk about the load regimes. And a remarkable co-evolution. So the only way the engine architecture can look like this is because you've got sort of nickel superalloys, single crystal alloys that work in the turbine, where the gas temperature over the surface of the blade is actually above the melting point of the alloy that we use, which is kind of pretty odd. So it's glowing white hot and it's got massive loads on it. And at the front end we do all sorts of horrible things to it in service. That can be operating down at minus 40, minus 50 centigrade, all kinds of high strain rate, high energy events and things in there. So the materials evolution has been incredibly important, but it's not just that it kind of works some of the time. We've got to have phenomenally good predictive capability, and there's two reasons for that. One is the product's got to be boring in service. The chief engineer should just, once the product's certified, should have the easiest job in the world. In reality, it's not quite like that because it's very complex. The operators may do things to the product that we weren't anticipating, and the material may behave in different ways from what we're expecting. And that's because, partly, a lot of the conditions that we get in here you cannot reproduce in the lab. So let's take this at max flight conditions, and this is white hot in the middle. And let's say you have a flame out, you're flying along at 700 miles an hour. You've got huge airflow through this and massive thermal heat sinks, and you can have all kinds of temperature inversions and things going on in there. Pilots don't generally like the engine just windmilling round, so it can chill right down in a couple of few seconds. They then squirt a load of fuel in, so you can have massive thermal mechanical fights. You can actually have situations where the thermals beat the mechanicals in terms of the stress. So even though the thing's winding up because you're dumping in megawatts of power, it's actually getting hotter faster than it's rotating in terms of stresses. So all kinds of complicated things. So that's why predictive capability is very important. I need to speed up quite a lot now, so you've got to bear with me. So I've spoken a little bit about new product introduction. I've said that the product is reliable in service, and I won't dwell on that anymore. But we do have in-service problems, and they should be really, really hard, because if they aren't, if you've got an in-service problem, and they can be huge as well, absolutely enormous. 100 million is sort of like a big service problem. And at any given time, you might have a couple of those on your hands to work through. If it's easy and you've got something that goes bang in service and you have a look at it and you kind of go, oh yeah, we thought it might do that. We haven't designed it properly, okay. So what should happen, and what happens most of the time when you've got a service problem, is you look at it and you go, wow, this is really, really complicated. And then one of the other parts of my job is then to look at big problems like that, technical problems, and try and scissor them down into chunks where I can then, at least it wasn't my phone, you can scissor it down into chunks and go to different bits of the company and different universities in the UK around the world to say, here you go, here's a package of work that relates into this, and then it's the Rolls-Royce job to try and assimilate all of that into a solution. And quite often the clock's ticking as well. So you have, in the event of major problems, if they potentially affect product reliability, we have to demonstrate that we're an acceptably good position with regard to what's called product reliability, essentially safety. And if we aren't, we then get into some quite unpleasant things, which can include grounding fleets. So we can say, well, actually, we're not at an acceptably reliable level. You've got to ground all your Boeing 777s that have got our product on them. You're not going to be very happy about that. And it gets quite serious quite quickly. So that's this bit in here. And one of the key things there is that when you get stuff like that, you cannot be starting from first base. You've got to be right at the front with it all. You've got to be driving the research, driving the understanding that helps you with predictive capabilities for problems that you don't actually know you've got yet, but could be the next phone call. Okay, so that's a very, very kind of dynamic environment. So that's existing product portfolio, new product strategy. They feed into requirements for modelling, experimentation. We then feed some of that into academia, normally with some research, normally quite a lot of research gearing. From an academic standpoint, you get all kinds of fun stuff there with advancing a knowledge. We get a thing where we better understand what's possible, so that when we make that bid to an airframer, we can kind of say, all this stuff's going on, we think we can do this. And we also have the potential of a rapid fix for in-service problems. Still going to cost us, still going to be hard, but we're not starting from first base, which is what will give us problems. Right, let's go on to some more technical stuff now. So if you actually think about the time, temperature, lengths and cycles, I've tried to put all this onto one slide, that our materials actually experience. It's quite remarkable. So if you start off with time, you've got products that are going to be out there for years in quite complex load regimes, going through cycling, you know, temperature, stress, environment, all the rest of it. So you're into days and years in there. There's some fatigue mechanisms that I have not got time to go into. They're fascinating. We're doing all sorts of fun stuff on it. Spent millions on it, a thing called cold dwell fatigue, where you get time-dependent behaviour in materials and understanding how that works. So that's seconds to minutes. We then got FOD and impact, where occasionally we have things like birds or stones or all kinds of bits and pieces, sometimes bits of engines going through engines. And given that the tips of the blades can be going supersonically, and you've got a hard metal on metal impact, the strain rate at the beginning of that's actually singular. And then we also use some fairly advanced processing techniques for metals, one of which is laser peening, where you use a high energy laser. I think it's about 7 nanosecond pulse we put on the surface. You drive the surface into, you yield it in tension, and then substrate pulls it back into compression. That optimizes the fatigue behavior. Then in terms of numbers of load cycles, we've got everything from one load cycle, and I'll show you an example of that in a video in a minute or two, through to ultra high cycle fatigue, where if you've got resonance in components and the American military NSIP lifing requirements, you've got to come up with estimates of the material durability at 10 to the 9 cycles, 10 to the 9 load cycles. And you may think, well, yeah, but you're never going to experience that. If it's incorrectly designed, one flight from London to New York, if you've got a small aerofoil on resonance, will clock up 1 million stress cycles. It's just, you know, tuning forks. And we've got the ultimate machine for shaking tuning forks. It's like, you know, driving through the middle of a city with, you know, a whole boot full of them, and you wonder why they rattle and vibrate. And to give you an idea of some of the fun stuff that goes on there, for some of our military products that best remain nameless, we might look up to the 40th, 50th resonant mode in an aerofoil, and then have to look at all the different engine mechanical and aerodynamic interactions in terms of the forcing functions of whether or not we're going to see that. And they're really there's one, this doesn't give it away, but there's one on one of the very important military programs that we did that was called the dancing frog mode, because when you looked at it, you go, it's a frog. And then you run it with time, its feet. Length scales, everything from meters, residual stresses, macrozones in material, I'll explain a bit what they are in a minute, through to crystals, metallurgists call grains for some reasons. And that's microns down to millimeters, and then down into precipitates and faults, and I'll talk a bit about that. Very important for both aerospace and nuclear, so we're in amongst the atoms, and I'll talk about that. And then in terms of temperatures, I've said everything from cryogenic right up to, there's some really neat stuff I could talk about cryogenics, but I better not, right up to the thing glowing white hot in the engine. So this is a bit where it all starts to unravel, because so far you've been thinking, well, yeah, physics is okay, kind of do physics. Metallurgy can't be that hard because it's kind of like crystals, and we know about crystals. Right, could spend days on this. The colours in here are you can see the morphological shapes of these things, yeah? So this one's got loads of needles in it, this one's got lots of little round blobs. And the colours are actually the crystal orientation, crystallographic orientation. These are both titanium alloys. And there's loads of neat stuff about how these form and grow and do stuff. But what I'm going to try and explain to you now is that the complexity associated with this is absolutely amazing. It has huge knock-on effects to the mechanical behaviour. So what you find is that the crystallographic and morphological orientation of these things actually depends a lot on, surprise, surprise, all kinds of pretty neat physics principles. So you get certain orientation relationships of parent and daughter phases in there. And you can get certain subsets of the allowable ones for various reasons. And these things can all kind of talk to one another, and I'll describe about how that works in a minute as well. The other thing I want to try and get across to you is that in this one, you'll see that you've got little blobs, and you've also got bands of colour. And these actually correspond to crystallographic texture evolution when you process materials. So effectively here, we've got a composite on many different length scales. And the really neat thing is that what it chooses to recognise as a significant microstructural feature depends on the load regime. Okay, so if I was doing a high cycle fatigue, fully reversed cycle, it would be one of these things in high cycle fatigue. It would be one of these little blobs that I would measure and correlate to my properties. And I'll go, oh yeah, if I make these smaller, the high cycle fatigue gets better. If it's notch fatigue, where you've got plasticity and other things going on, it actually then jumps to being the misorientation between the larger length scale things. So the material is actually quite fickle, and it can behave in different ways depending what you do to it, and what you need to measure and what you control is dependent on the load regime. There's loads and loads and loads on this, so let's try and get to it. So one of the other things that's a bit unsettling is that deformation. Here we've got dislocation. In metals, it's mainly dislocation and twinning, right? So you get this thing where it's dislocations that mean that the metal's actually got a strength that's a lot lower than you thought, but it also has huge amounts of ductility. And how these things move around are really, it's phenomenally interesting, how they interact with one another, whether they form loops, you know, what goes on is really quite neat. And the other thing I'm going to tell you about, which again is a bit disturbing, is that if I took a bit of metal like that and said, right, I'm going to stick it in a test machine and I'm going to force the crosshead in the machine to move at a given rate, I'm going to generate a tensile strength, right? So you think, yeah, okay, sounds pretty mundane, doesn't it? And just for arbitrary reasons, in that it's quite a useful time to test it in, you might choose to do that test in a few seconds and you'll get a result of X. So let's say on our titanium alloy in the previous slide, we're at about 1,000 megapascals ultimate tensile strength. So that's okay. Instead of doing it in a second, I'm going to do it in a millisecond. What happens? It's actually stronger. Ah, interesting. And the failure strain doesn't change. So let's do it in a microsecond. What happens? Oh, it gets stronger still. And you actually find you've got a log linear relationship there with the strength and the strain rate that covers about 8 orders of magnitude strain rate. I can go on and on and on about that. But then it gets even more fun. So you've got this thing where you go, oh, this is good, because it gets stronger and stronger and stronger. And then you get a point where it goes sort of up, almost like an exponential rise. And that's where you actually treat this thing, because it's got mass, because it's got what's called a Burger's vector. So there's a unit of material here. It's got a mass, and it's got a velocity. It's got a kinetic energy, okay? And you can't drive things plastically faster than the elastic wave speed in the material. So it's a beautiful, encourage you to read it. 1955, I think, a guy called Weertman came up with the theory of why the strength goes exponentially up to the ionoelastic limit. And they essentially treat it like special relativity, and they say you can't go faster than the wave speed. And as you approach the wave speed in the material, your kinetic energy becomes infinite, and it actually all ties together. Right, won't talk any more about that. Dislocation's really neat. So, get on to some more sort of physicsy stuff. So, said that dislocations are important. So there's all kinds of different things you can do to have a play with this. So from a modelling standpoint, you can do things called molecular dynamics, which is where you look at the kind of like the bond order associated with the atoms, which gives you a feel for what's actually going on in the dislocations. And I think it was a physicist that said about the devil created the interface, and that's absolutely true. So you find that if you read any of the textbooks, they'll talk loads about dislocations moving about within crystals, but as soon as you get to all the fun stuff about what happens at boundaries and interface, it all starts to go rather kind of quiet and embarrassingly not much spoken about. So this gives you some ability to have a look at what goes on here, but it's quite limited because you've got to do it essentially infinite strain rate, and there's various other concerns with that. So this is some work we've been doing with, I'm going to run out of time, with a guy called Dongxing Zhu in IMR. Absolutely amazing character, runs the molecular dynamics group there. And one of the first meetings that I had with him, we went out and we had some lunch and we were wandering back, and he sort of goes, oh, yeah. He says, you've got to see this, you've got to see this, you've got to see this. And he kind of kicks the door open on this thing. And there's a computer in, I'm not into computers, but a computer in there about the size of a transit van, right? And state of the art, he said, commissioned last month, state of the art. So I'm like, oh, yeah, very impressive. It's just like got the one green light on it, you go like, okay, yeah, it's very good. And yeah, okay, I'm impressed. It's big, it's got to be good, right? And then this dark thought crossed my mind. I said, so how does your group go about bidding for time on this machine? Because it's probably a bit like the UK, that you might get an hour every 2 months or something on it because there's a bid process. And his face fell and he goes, no, he says, you don't understand, this is the 4th of these from my group. So he's got 4 of these big whizzy, and they would be state-of-the-art machines for doing all this stuff, right? Right, molecular dynamics. So we're on to real things now. So one of the incredible things that's been going on is the fact that modelling and experimental techniques, last decade, unrecognisable, and it's accelerating. So what we've got here, all the action in materials, the majority of materials derive their strength from length scale, not from chemistry per se. Okay, so if I take an alloy and I throw in elements to it, you'll get some strength contribution from solid solution or interstitial strengthening, which is just the atoms sat there interfering with the dislocations going past. But the bulk of the strengthening actually arrives from length scale. So if I took this and it was a single crystal, and I bent it and I got a strength of X, you kind of go, well, yeah, okay, very interesting, Dave, go away and do something useful. So I make it smaller and I do it again. So I halve the size and I do it again. I get pretty much the same answer. It's like, okay, Dave, you're really boring me now. Once I get down to typically about 2 or 3 microns, I suddenly find then that the strength of the material starts to go up dramatically. Okay, so single crystal, no jiggery-pokery, length scale strengthening to do with how dislocations interact with one another when you've got a plastic strain gradient. So wouldn't it be kind of quite nice if we could actually do that with having to try and back it out from this horrible thing with billions of crystals in it that are all interacting with one another? And by the way, we don't have particularly good stats on the misorientation distribution functions as a function of length scale and all the rest of it. Even for a single phase material with 2 grains, if you look at all of the degrees of freedom that you've got in terms of tilt, twist, rotation, crystallographic and morphological, if you explored all those in 5-degree intervals, you've got about 1 billion combinations just in one boundary, and we've got billions of grains in here, and we might have 4 or 5 phases, distinct phases. So the complexity is phenomenal. So wouldn't it be nice if instead of having to try and back all this out, we can actually measure it directly? Well, that's what we've got here. So this is a stress strain curve where we take a bit of metal and we bend it. But look at the loads there in micronewtons, displacement in nanometers. So this is micromechanical tests. So we've got a lot of work going on here. Well, all over the place, but this is with Angus Wilkinson in Oxford. And you can take these things down to less than a micron across, and you can actually bend them. You can bend them and you can twist them and you can press them, and you can get data out. So in titanium alloys there, we can say, oh look, once we get down below 2 microns, that's where we're starting to get into strength, and we can decouple chemistry and length scale effects in that. So that's kind of quite cool. Some neat experimental kit that drives that. You can then take those and you can, so they're triangular shaped things. If you imagine a cross between a diving board and a Toblerone, and you load the end. In this case, we've got a dual phase material. So we've got HCP phase there and a BCC stripe in the middle. These things are slip bands, you can see. We can then take that, because the samples are sufficiently small, that we can look at it in a transmission electron microscope, and we can see all the dislocations that are left there. So a lot of the ones that have actually done the work and given the deformation have gone, but we can get some idea of what's going on. So that's kind of quite cool. We can also go to discrete dislocation modelling and actually model that whole sample and look at where the slip bands, because the dislocations all talk to one another, and you get these things, planar features in here. You can actually have a pretty good go at modelling that. So there's a convergence where it's small enough test piece sizes that it's tractable, certainly at molecular dynamics, at discrete dislocation level, to get real numbers out. Right, I haven't got time to talk about this, other than to say strain heterogeneity is really neat, and digital image correlation. You can actually, these things are called slip bands, so that's the dislocations working together, multiples in planes, and the length scale over which you've got to look at heterogeneity within a material and how it all talks to itself is really, really neat. And that's just beginning to unfold in a big way now in terms of understanding material behaviour. So we can go down a level still, and this is some really great fun work we've been doing with Andy Miner and co at Berkeley. So that's a US National Lab for Electron Microscopy. And they can go a step further. So what we've got here is this little tensile test. Remember I was saying about my pen, if I make it small enough, stuff gets interesting. So these are 200 nanometers across. They can pull them so that you get a stress strain curve. which is pretty neat in its own right. That's 200 nanometer scale bar there. But they can do it inside an ultra-high resolution transmission electron microscope. So you can actually watch the dislocations moving around in there, and you can relate that to what's actually going on in the material as to whether we're forming things called twins, which is a crystallographic shear process. So we've got micro twins in here. Transmission electron microscopy's gone through an absolute renaissance even in the last 5 years. So these are ultra high res TM images. It's an HCP crystal structure. They're columns of atoms that are imaged. And if you can kind of believe me, you've got a thing in the middle there that's actually a region of short range order where we've got Ti3Al forming, which again significantly alters the properties. Another technique we use is UK world lead, pretty much world leaders on this, which we've used in anger for service problems, and we published that as well. It was a thing called atom probe tomography, where you take a needle of material, you apply a big electric field to it, and then you pulse it either electrically or with a laser fairly quickly. You've got a grid around the inside of the machine, electrical grid, so you know where the ions that come off hit, and because you've pulsed it, you know the charge, you know the time for it to hit the thing, so you know the charge to mass ratio. So essentially it's a spatially resolved mass spectrometer, and you get about half the atoms. So we've had stuff out of engines where we've literally torn it apart atom from atom and then built up the full 3D atomic map of what's in there. And that allows us to understand the chemistry of interfaces and the chemistry of very, very small precipitates, which can be critical in dictating behaviour. I really need to accelerate some more. So other things you can do, this is a little bit on nuclear. So one of the things you find there is that things don't work quite the way you expect. So iron in zirconium moves around as an interstitial, which isn't what you'd expect because it's a damn great big atom, and it moves like blazes. So it's going really fast, and what you can see here, they can actually image iron moving down boundaries, and that's a 4 nanometer length scale bar. This is, I should mention the groups. They should all be on the slides, the people that I'm interacting with on this, where we've got programs running. This is Michael Preuss and co at Manchester. Really lovely work on that. Atoms matter in engineering. The slide that I showed you at the very beginning, I will just go back to that. I'll regret this one, but I will go back to it. It's quite incredible because you kind of go, yeah, Dave's on about atoms again. That's a CANDU reactor. I had a while on a Royal Society fellowship, one of the fellowships, in Canada, and while at Chalk River, which is Central Nuclear Research Facility. Canada uses CANDU reactors, that uses natural uranium and heavy water. These things are 4 meters long, and those dislocations that I was telling you about can form loops and things in different places depending on the fluence and all the rest of it that you get in there. And they can then combine and do stuff. And the bottom line on that is that through life, that 4 meter long tube will grow by about 2 inches. Okay, sorry, mixed units. So if you're an engineer then, you're kind of going, right, so why does it grow like that, and what are the variables that make it grow? And it's all about the crystallographic texture and all those kinds of things. And then from an engineering standpoint, so what are you going to do then? Are you going to make that so that you go, right, all right, they're going to get longer and the tubes are going to bend, and then the guys have got to pull harder when they want to get things in and out of them? Or are we going to make the ends of the reactor a bit floppy? And when I look at this materials guy, or this physicist, or this modeller, who says, yeah, it's going to get 2 inches longer through life, trust me, does he actually mean 6 or 1 or none? Or, and okay, so if you're telling me then that these are going to get, are they all going to get longer by the same amount? Or are they not? Because if they aren't, then you've got real problems, right? Because it's kind of, anyway, you see where I'm coming from on that, right? So I need to get a move on to get through the rest of the talk. Right, so I've spoken about sort of university lab type stuff. The other thing that's absolutely great fun, national facilities. And synchrotrons, so we've got a nice one in the UK, Diamond Light Source. You can do all sorts of fun physicsy things there. And I've got the last 3 or 4 slides are on some stuff we've been doing at the XFEL at LCIS in Stanford. So several different things you can do. At first pass, you can actually have some great fun putting in situ loading rigs inside synchrotrons. You can do tomography, so you'll know more about that than I. So this is actually a crack front. You get phase contrast imaging, so the light and grey there is actually the microstructure of the metal. You load the thing in different ways, you pull it around and wiggle it, and you can watch the cracks propagate and you can see how they interact in 3D. That's important because when they're near the surface, they behave differently because you've got different constraint. So that's actually quite enlightening in its own right. You can get to high spatial resolution with it. You can also punch through quite a lot of material. So we can stick photons through about 4 or 5 millimeters of titanium, something like that, which is getting quite useful size. So that's okay, but it's not the be all and end all. We like stress, understanding stress. So what you can do is to use the atomic spacing, the lattice spacing of strain gauges. Then when you drive the material around stress strain loops, this is in compression, this is stuff at out Queen's, spent some time there as well, which is great fun. You can look at the lattice strains, see when they're loaded elastically or when they're effectively not going up in strain as a function of load, and then you can see how they all kink and interact. So that gives you family distributions for certain orientations of grains of whether they're elastic or whether they're plastic and how that changes with time, but it doesn't tell you anything about the actual individual grains. Other things we can do, combine tomography with the lattice strain stuff. So this is silicon carbide metal matrix composites. This is a real sample as well. They took, this is Phil Withers and Co. That's done at ESRF in Grenoble. So these things are about 100 microns diameter, silicon carbide fibers. There's a crack in it. The colours are the stress in the fibre. So you've got micronish resolution in terms of the tomography stuff. And you can see how the fibres interact with the stress rate at the crack tip to see whether or not this thing works in the way that it should as a metal matrix composite. Okay, so that's taking it a step further on where you're saying we've got topographical information and we're combining it with lattice strain stuff to get stress. Right, very, very quick, promise. Other fun stuff we've been doing, this is with physics at Nottingham, a thing called SRAS, spatially resolved acoustic spectroscopy. We've been working with them now for quite a few years. And they use a laser to excite near-surface waves on surface of metals. You can then use another laser to measure the input signal. It's quite clever the way they do it, but the bottom line is you can measure the wave velocity. The wave velocity is related to the modulus, and modulus related to crystallographic texture. So we can do crystallographic mapping of surfaces very, very quickly without having to cut it into small bits and put it in an electron microscope. So this is all really good fun. So this is actually an ingot slice. And you can see there how the grains form, what goes on. We can look at things over big length scales, we can get better statistics. This is a forged disc, and you can see there all the different grains, and that matters to the properties, which I think I've explained before. Right, oh, watch this, there you go. So that's 20 million quid, please, to do that test, give or take. Final test that we do, fan blade off, and what we have to demonstrate is that that blade is safely contained within the engine. So the total kinetic energy and the energy density, where that impacts on the case, same order of magnitude as tungsten long rod penetrators they use to destroy tanks in the military. We haven't got 70 tons of armour, we've got a few hundred kilos, which makes life quite challenging for us. You'll see this in higher resolution here. And we don't like getting this test wrong. It's share price sensitive when we do the test, because if it's wrong, you know, we've not got months and months and months where we're waiting around, sat with our feet on the desks. This is the final test. The expectation is this goes right. We've got customers waiting for our product on wing. And if it doesn't work, we don't just kind of go, oh, actually, thought that might happen, not going to go down well. So a lot of modelling capability in that, understanding material deformation at high rates. One of the things I didn't tell you before when I was talking about high strain rate behaviour is that you get the strength things quite easy to, relatively easy to understand. When you run it to high strains at a high rate with a high plastic strain gradient, you can get runaway reactions in the material where the dislocations are hot, right, because they're atoms bumping over one another. So that heat, if it's happening so quickly that as soon as you've got flow instabilities in the material where the heat means that the flow stress drops, which means that it flows more readily in that area. And what you can see here, this is normal structure in our titanium alloy. And what you've got here is bands where it's started to deform, and because it can't dump the heat, you can have bands in here that are only, you know, tens of microns across where the metal can actually go molten in a band about, you know, 10 microns wide. Over here, it's completely unaffected. So as you go up in strain rate, you get the same thing if you're firing bullets at stuff. As you go up in strength, it looks better and better and better and better until you reach a point where it just looks as though it's shattered. Okay, and that's what we've got here. It's called adiabatic shear band formation. So that's quite important for us to understand how that works and what goes on. There's loads and loads of stuff I could talk about this, not got time. Really, really interesting phenomenon, and combined with twinning as well, where you can see some twins in here. They happen at sonic velocity in the metal. So titanium is about 8 kilometers a second in one of the dominant orientations. So you've got this thing where, under normal circumstances, if you're trying to infer all this after the test, it's like if you've had a huge car crash on the motorway, multiple pile-up that's then caught fire, and you're coming along the following day, and from the heap of ashes, you're trying to figure out what the driver was doing on his mobile phone when he crashed. Okay, so it's really, really, really tough. So wouldn't it be neat if, right, sorry, another slide, not just during service loading, when we make things, you get adiabatic shear band. This is machining processes where you've got a milling machine or a lathe and you wind a cut tool into it. These are adiabatic shear bands. So locally, you've got very, very sort of interesting things going on at surprisingly high rates. I haven't got time for this, I promised I would. One of the other things we've been playing with is, which is related to this, high-speed X-ray flash photography. This is at STFC, at the Vulcan facility. And we've had some bits of metal we've poked into here, and they use laser optical driven X-ray flash. So you hit a foil of metal with enough energy, it's lots and lots of energy, lots and lots and lots of energy. When you whack the surface, you strip all the electrons off all the atoms. You then get all kinds of interesting things with the electrons trying to get back in again. And you get a stonking great big X-ray pulse that's obviously dependent on the target foil. So we can be down at sort of picosecond-ish duration, which is quite useful if you want to temporarily resolve things. And they've done some quite neat stuff with that, so we're playing with them. But the final bit I want to get on to, that's still too slow. Picoseconds actually very slow in relation to something moving at kilometers a second when you want to resolve it over sort of micron-ish length scales. You'll probably have seen this, but really, really neat piece of kit. So you have an ultraviolet laser, shine it off a mirror, hits a copper plate, the copper plate goes have some electrons. You get a bunch of electrons, and being physicists, you've got to accelerate electrons, right, because that's what you do. So you accelerate the electrons, that's all good fun. You then have the thing where, and one of you can explain this to me, why when you bend relativistic electrons, they decide to give you X-rays, and it's got to be more comprehensible than just saying, oh, it's conservation of angular momentum. Rather than bend them the way you do in a synchrotron, you can wiggle them, so that's a wiggler. Incredible in terms of the actual setup of these things. So this, in the kit that we used last year, the wiggle is 200 meters long and the magnets have got to be aligned to within about is it 8 microns or something. Absolutely incomprehensible. So X-ray laser, so the photons jump from bunch to bunch on the electrons, you get constructive interference. And that's the reality. So this is LCLS at Stanford. That's the start of your electron jiggery-pokery. That's the accelerator tunnel. Those are your target stations down at the end there. And I had again, on one of the fellowships I was on, the Royal Society one, great fun. A whole day around that facility with the guy that runs it and his first line. And this is me saying, I don't normally put, but this is me saying, yeah, but it can't really work. And him saying, yeah, it does. Trust me, Dave. Look, that's the exfil spots up there. So we put in an application for beam time. Open access like synchrotron facilities, and we got 3 days beam time allocated to us. That'd be broad brush numbers, about $3 million worth of beam time on that, paid for by the American taxpayer. Don't know if we've got any Americans present, but thank you if you are. And this is really cool bit of kit because the physics story, when I sat there at the beginning, I'd read a bit of the stuff about it. I had an idea of what I actually wanted to do on the kit. And I said, okay, so when you say it's somewhere between sort of 7 and 12 femtoseconds for your imaging pulse, what actually is it? And the techie guy sort of like, oh, this, and he leans back, and I kind of thought, it wasn't meant to be a hard question, it's kind of like, where are you? And he goes, oh, well, he says, it does actually start getting really quite complicated because it depends what you mean by time. You're a physicist, you know all this, but femtosecond is a minute is the age of the universe. So this really is short, light can only travel a few microns. So that means your sonic dislocations and your twins and things might as well be glacial. One of the other things that's neat about this, the molecular biologists use it a lot for getting diffraction of viruses and proteins and all that kind of stuff. It's called diffraction before destruction, because you pump in so much energy into your sample, boom, it's gone. But you get the diffraction information before it destroys itself. So it's like the thing with the galloping horses and the photography and the debate about, you know, whether all the hooves are off the ground, but you shoot the horse each time, so you've got to hit a different target. It's doing 99.79s the speed of light, so you get 20,000 times relativistic length scale effect, 12 billion EV, 10 kiloamps, so you've got a terawatt of power when the pulse is coming down the tube. And when they designed this, it's really quite neat, because they got quite worried if they had a power cut when they had got the electrons quite a long way down the tube and you flooded the target stations with relativistic electrons because you didn't bend them out of the way with an electromagnet. So they've got a huge permanent magnet that they bend them down into, so that all you've got to cope with is the X-rays. You get 10 to 12 photons in a burst, so it's about a billion times brighter than a synchrotron, but it's a short duration, so you've got to trade one well enough against the other. And this went from concept, it was a sort of Star Warsy type idea, first light in less than 20 years. You can't do subscale testing of it. You can test some of the bits, but you can't actually demonstrate the whole thing. And they switched this on and essentially it worked. They were absolutely amazed. The project director, she got a call at 2 o'clock in the morning after they'd got the vacuum levels down, and they're like, right, now start several weeks of work. And she got a call at 2 o'clock in the morning and said, we've got first light on it. And she thought they were winding her up. So we got our, the thing that I'm interested in, on the target stations, you can combine the XFEL with an optical laser, so you can shock material and then you can study what's going on in it for, you know, with whatever delay you want. Frustratingly, the thing I really wanted to do, they couldn't do then, but they probably can now, which is to beam split the XFEL, because I want to get a dislocation multiplication. So you whack it with the optical laser, you hit it with an XFEL beam, and then if sort of, I don't know, few femtoseconds later you hit it with another one to get the individual dislocations and see if they've multiplied. You've got issues with detectors and things on that. So anyway, that was really, really good fun. So we've got the tools, we've got the models. Do we have the brain power to do anything useful with them? And that's the limiting factor now, and it's really quite scary. So we can't blame lack of experimental facilities for what we want to do. We can't blame the computers, we can't blame the models, because all that's... Sorry, one other final thing. I haven't mentioned atomistic modelling, and we're interacting with 3 groups around the world on that. That's showing huge promise. You've got to ask the right questions. Density functional theory, DFT calcs, very, very powerful. But the key thing, and what's limiting us and what will continue to limit us, is actually people thinking. And that may come as a bit of a shock, but that's absolutely true. It's people thinking about what they're doing. Sure, we can run away and do loads and loads of work and have fun doing it, but actually thinking about what the path is through to get to the knowledge that we need. Could physicists help? Yes. I'll come back to that in a minute. Final 2 slides. So we're now into sort of off the technical stuff. What do I look for in recruits? So sorry, it's a bit wordy. I want people that can think. I want people that, when we've got some big new thing that we don't understand that's really complicated and it isn't in any textbooks, and when you ring round all the senior profs around the world that you know on a given subject area and say, if this then da-da-da-da, what happens? And they don't know, you know you're in for a really quite interesting time. And then you really want people that can apply themselves and can think and can kind of try and figure out how it all fits together, understand what's going on. Go on, this is a little bit tongue-in-cheek. Go on, atoms are easy. Continuum mechanics, on the other hand, is really quite easy. Very useful, don't get me wrong. But the complexity, from material science standpoint, the complexity in terms of the interactions of all the things that are going on in there is phenomenally complex. And we need maths in that as well. That's a big weakness at the moment. Not from a Rolls-Royce thing, but generically, of understanding statistical, properly understanding statistics of materials that we use. Also, I'm after people that are actually enthusiastic and want to come in and do stuff. If you get into your career and it ends up being like some kind of strange cross between One Flew Over the Cuckoo's Nest and the Shawshank Redemption, you're doing something wrong, right? You have the power of choice. Every morning you get up and go to work, you can write your resignation letter. Every morning you can do that. You choose to go to work to do something that you want to do. If you're not enjoying it, do something else. Do you really value your life so low that you're prepared for this to be some sort of warped prison sentence? Anyway, don't start me off on all that. I don't really care about your starting discipline as long as it's something sort of technical. Ideally, if you can do sums, that's great as well. The reality is, I'm after the basic toolkit. Can people think? Are they bright? Do they understand how to tackle problems and break them down? Reality is, even if it's a narrow materials role we're looking at, it's 2 to 3 years after you bring somebody in before they're really beginning to get their head around what goes on. And it's probably about a decade before they'll get to sort of specialist type level, because a lot of it's knowledge and understanding how stuff fits together. But you've got to have the enthusiasm, want to do it. People skills, don't mind if you're quiet, don't mind if you're lacking in confidence, that's fine. I'd far, far rather have that than somebody either that's going to hack off all the people around them because they're abrasive, or a really worrying one in a technical environment where we've got safety critical product is anybody that's overly confident or arrogant. Then you've got a real issue, because if things are very busy and all the rest of it, you've then got the potential that their capability may actually not be matching their level of confidence. And you've got to be really, really careful about that, because there's no room for error in this. If you get stuff wrong, it is very, very bad. Seriously bad. So although I've been very kind of flippant and light-hearted going through it, this is all because it matters. I don't know if any washing machine manufacturers here, but if it was washing machines, we wouldn't care, we wouldn't be doing the sciences, because we've really got to get it right. I won't dwell on this, but from a company standpoint, it's basically all online unless it's direct entry. Direct entry is if you've got a PhD. Again, online in terms of the application, but rather than going through a grad assessment scheme, you'll get interviewed by technical people for a specific role. So the key message for you really, when in job ads, and again this is generic, not just Rolls-Royce, when it says degree in XYZ or appropriate technical discipline, if you're a physicist, and actually to quite a large extent as well if you're a mathematician, this probably means you too. A lot of people get really bent out of shape about, but do you have physics jobs? The technical complexity is enormous, and we have loads and loads of roles where there's no degree discipline that would actually match onto it one for one. We want people that are bright, people that can think, people that have got the basic toolkit. So that's it. So I've run over a bit, but
okay, thank you very much.
right.